In today's video, we are going to be discussing alkanes, and here we have the outline of what we'll be discussing. What are alkanes, substituents, alkyl groups, organic nomenclature, isomerism, representation, properties, chemical reaction, and uses of alkanes. So first on our list is what are alkanes? Alkanes are saturated hydrocarbons. In the first video of this series, we looked at the classification of organic compounds, under which we saw that organic compounds can be divided into cyclic and acyclic, as well as hydrocarbon and non-hydrocarbon. Now, alkanes happen to fall under acyclic organic compounds in that they have open chain. Their structure is in the form of an open chain that could be branched or unbranched. They are also hydrocarbons, meaning that their constituent element is carbon and hydrogen. Now, alkanes form a homologous series, and a homologous series is basically a family of organic compounds with the same general molecular formula. For alkanes, the general molecular formula is in the form CnH2n plus 2. So if n is equal to 1, then we would have CH4. This is the first member of the alkane group, and it is called methane. Now, a homologous series, as I said earlier, is a family of organic compounds that have the same general molecular formula. This family of organic compounds also exhibits similar chemical properties, and this is due to the peculiar or particular functional group possessed by such homologous series. Now, for the alkanes, the functional group is a single bond. So the carbon-carbon bond is a single bond, the bond that exists between any two carbon atoms in the alkane group of organic compounds is a single bond, and in terms of hybridization, they exhibit the sp3 hybridized orbital. This is the general idea of what alkanes are. Firstly, we stated that they are saturated hydrocarbons. They form a homologous series that have the general formula CnH2n plus 2. The hybridization is sp3, and for the functional group, there exists single bond between the carbon atoms. Now, what it means for organic compounds to be saturated is that the bond between the carbon-carbon bond is a single bond. That is the whole idea of saturation. And a more in-depth definition would be that it cannot undergo addition reaction. Take for instance, if we say something is saturated, it means it cannot contain more of a substance. More substances cannot be added to a saturated environment or to a saturated solution. So in order to add anything in any form, some things would have to be taken away and then replaced. This form of reaction or this form of interaction is a substitution rather than an addition. And so for alkanes, they are not able to carry out addition reactions because of the saturated nature. Now moving forward, we want to look at the idea of substituents. So what are substituents? We have already established the fact that a hydrocarbon is made of carbon and hydrogen. Carbon and hydrogen. However, due to the fact we also have established that alkanes are able to undergo substitution reactions, and in the process of substitution, what happens is that other elements can actually be substituted into the alkane, such that we do not only have carbon and hydrogen, but other elements are part of the constituent elements. These other elements could be halogens such as chlorine and fluorine, and in a case where we have other elements other than carbon and hydrogen, such elements are referred to as substituents. Substituents because they have substituted hydrogen in such alkane or in such hydrocarbon. Now, as I stated, chlorine and fluorine are just a few examples of substituents that we might have. Now, another substituent, or another way in which we can look or consider substituents, is that given a particular carbon chain, so given a particular carbon chain or given a particular organic compound. Now, in naming this organic compound, we're still going to look at organic nomenclature, but in naming this organic compound, we consider the longest continuous carbon chain. Now, in this case, the longest continuous carbon chain is, of course, this. This is the longest continuous carbon chain. Now, if we have a branch with another carbon like this, if we go this way, from here to here, we would have 4 carbon atoms, and this is not the longest. If we go from here to here, we would also have 4, but going directly straight would have 5. So this is the longest chain. Now, this branch that has been formed here, so any other carbon atom that is outside the longest chain also serves as a substituent. So apart from the fact that the substituent could be a halogen that has been substituted for hydrogen, it could also be any other carbon atom or group of atoms outside of the longest carbon chain in a given organic compound. Now, this brings us to the idea of alkanes, of alkyl group. So let's briefly look at what the alkyl group is all about. Now, the alkyl group has the general formula CnH2n plus 1. It has one less hydrogen than its corresponding alkane. So if N is equal to 1, then we would have CH3. Now, the alkyl group of radical, it doesn't exist as a stable compound. It actually exists as a radical, and so this is methyl. It's the corresponding alkyl for methane that we have looked at, and it doesn't exist in a stable state. It's actually attached usually as a substituent to a longer carbon chain. So this is the whole idea of the alkyl group. Now, when we go further into isomerism, we would see that depending on the position from which the hydrogen is removed from the alkane, a given alkane can actually form more than one alkyl. in terms of isomerism. Now, moving on to organic nomenclature. From our outline, what we have next is organic nomenclature. So, what is the whole idea of organic nomenclature? So, there is an organization, the IUPAC, which is the International Union of Pure and Applied Chemistry, or chemists. Now, this organization has come up with the way in which to name organic compounds. We have the common name. Most of the organic compounds have the common names by which they are called, and they also have the IUPAC name, or the scientific name. Now we are going to be looking at how to name a compound, or how to name an organic compound in terms of its IUPAC nomenclature. Now there are 3 main steps that I would be considering under this. Now the first step is to identify the longest continuous carbon chain. The second step is to identify substituents. And the last step would be to locate substituents with numbers. So if we are given an organic compound like this, and then we have something like this, now carbon would generally form 4 bonds. Carbon is tetravalent, so it would generally form 4 bonds. Now, so we have our hydrogens attached here. This is not a substituted alkane, so all we have, it's a pure hydrocarbon, no other constituent elements apart from carbon and hydrogen. Now, how are we to name this given alkane? Now, the first step is to identify the longest carbon chain. So let's count here. If we take the longest carbon chain to be this, the longest continuous carbon chain, we would count 1, 2, 3, 4, 5 carbon. Now if we take this to be the longest chain, remember it must be the longest and continuous. So if we take this to be the longest chain, then we would have 1, 2, 3, 4. Now this is less than the 5 that we originally had. And if we take this to be the longest chain, we would have 1, 2, 3, 4. So it's quite evident that the longest chain is the one identified with the yellow mark. So this is the longest chain. Now, after identifying the longest chain, the next thing we want to do is to identify the substituent. And I earlier stated that the substituent is any other element, any other constituent element or group of elements that is not part of the continuous chain. In this case, we have this group of elements that are not part of the continuous chain. Now we can see here that this is an alkyl. It is CH3 and it has the name methyl. Now, having identified the substituent, we want to locate the position of the substituent in terms of the carbon to which it is attached. Now, how this is done is that we want to give this substituent a number, the lowest possible number. And in order to get the lowest possible number, we have to pick or start counting from a side that would help us to attain this lowest possible number. So I would just draw this out again since we have it's a bit. So drawing this out again, it looks something like this, and then the methyl is attached here. So if we start counting from here, we would have 1, 2, 3. So the methyl group would be attached to the third carbon atom. And if we start counting from here, we would have 1, 2, 3. So we can see that either ways the methyl group occupies the third position. It has the number 3. So this particular carbon or this particular compound is going to be named as thus. But before we look at that, it's good for us to take note of the fact that every organic compound has its name divided into two parts. So we have the prefix and then we have the root. Now the root is basically what tells you whether it's an alkane or an alkyl or an alkanol or a carboxylic acid. That is what the root name is for. The prefix, however, tells you about numbers. It tells you about numbers and positions. Now when we have one carbon, the prefix is meth. When we have 2 carbons, the prefix is eth. When we have 3, it's prop. When we have 4, it's but. When we have 5, is pent. And for the from 5 downwards, it follows the order of the Greek nomenclature that we already know. So this is going to be hex, and 7 would be hept, and 8 would be oct, 9 would be non, and 10 of course would be dec. Now the root, if we're considering alkanes, then the root is going to be ane. So in this case, since we have 5 carbon atoms, our prefix is going to be pent and our root is going to be ane. So this is pentane. However, it's not just pentane, it has a substituent, it has an alkyl group attached to it, and this alkyl group is positioned at the third carbon atom in the longest chain. So it's going to be 3-methyl pentane. This is how this particular compound is going to be named. Now let's consider some other examples. Now take for instance, we have something like this. Now since we know that this is a hydrocarbon, I would not be including the hydrogen atoms just to save time. But if we have a substituent, then I would include it. Now in this case, we have chlorine and bromine as substituents. The first thing to do, of course, would be to identify the longest carbon chain. And for this, we don't have to go through any route. We know that this, of course, is the longest carbon chain because there is no other carbon chain to be considered the longest. It has to be the longest and the continuous one. Now we have identified the longest carbon chain, so step 1 is ticked. Now step 2 would be to identify the substituents. The substituents here are chlorine and bromine as identified. Now the third step, so step 2 is done. The third step now would be to identify the position. Now in identifying the position, we want to start numbering in such a way that the substituents have the lowest possible number. So if we start from this end, we would have 1, 2, 3, 4, 5, 6. Okay, now you'd notice that the first chlorine here has the number 3, and the second chlorine has the number 5, and bromine has the number 6. So these are the set of positional numbers that we have. However, if we start counting from here, we'd have this to be 1, 2, 3, 4, 5, and 6. Now you notice that the positional numbers that we have in this case are 4, 2, and 1. If you look at these two sets of numbers very critically, you would notice that this set of numbers provide a lower position as compared to this set of numbers. So we would make use of this numbering. Now in making use of this numbering, when we have a particular substituent that occurs more than once, we make use of the prefix di, tri, tetra, and so on to indicate that this substituent appears more than once in the given compound. Now in this case, we have chlorine appearing twice and bromine appearing once. Of course, we don't have to indicate that bromine appears once. So in this case, how this would be named is, first we need to know that our substituents are bromine and chlorine. Now in naming organic compounds, we follow alphabetical order. So when writing out the name, bromine comes first before chlorine because B comes before C. So this compound is going to be named 1-bromo, 2,4-chloro. Now it has 6 carbon atoms, so we know that we'll be making use of the prefix hex and the root ane. So 1-bromo, 2,4. I omitted the di here, so this is dichloro because there are 2 chlorine, so dichloro. I will just take that out. So this is going to be 1-bromo, 2,4-dichloro hexane. This is the name of this particular compound. Okay, now we have looked at the 2 cases where there's an alkyl group and where there's a halogen substituent, and we have also seen that when the substituent appears more than once, we indicate that presence by using the prefix di, tri, tetra, and so on. And we also indicate the position, separating these 2 positions with a comma. If we had 3 chlorines, then we would have 2, 4, and probably 5 trichloro. And in a case where we have ethyl, for example, if we had ethyl and methyl, just to give us an idea, if we had ethyl and methyl as substituents in a given organic compound, ethyl would come first in the naming because E comes before M. So this is the general idea of the nomenclature, and more practice would help us understand even better. Now moving forward, let's look at the idea of isomerism. What exactly is isomerism? And what is an isomer? Isomerism now, from the word iso means same. So isomerism is a phenomenon. Isomerism is the existence of an element, or the existence rather, not an element but compound. Now isomerism is the existence of compounds, with the same molecular formula, but different structural formula. So when we go forward to look at representation, we would see that organic compounds can be represented in various ways. Now, when we are given the structural formula simply gives us an idea of the way the atoms are arranged in space. Now, two compounds may have the same molecular formula, like C4H10. However, the way in which the atoms are arranged in space may vary. For example, let's just take a look at C4H10. We could decide to have a continuous chain of 4 carbon atoms in this way. Okay, and we could also decide to have it branched out in a way that looks like this. Now in this case, we still have 4 carbon atoms for these two molecules, or for these two compounds. However, in this case, what we have is a continuous chain of 4 carbon atoms. However, here we have a continuous chain of 3 carbon atoms and 1 substituent that exists in the form of an alkyl group. This is the whole idea of isomerism. However, there are different forms of isomers or different forms of isomerism. We could have the positional isomer, or isomerism. We could also have the structural isomer or isomerism. We could have the geometric isomer, and we could also have optical isomer. For the sake of this video, would be considering the structural isomer only. So the structural isomer only has to do with the difference in the way in which the atoms are arranged in space. It has to do with arrangement, and C4H10 is a basic example of how this arrangement vary. So if we are to name this particular organic compound, how we would name it is that, of course, we would identify the longest carbon chain, which is this, or of course we could go this way, but either ways would still have the same name. So picking this as the longest carbon chain, then we would have our root name. Since there are 3 carbons, we would have the prefix to be prop and the root name to be ane, and our substituent here is methyl, and it is positioned at the 2nd carbon, so we would have 2-methyl propane. And if we are to name this is simply going to have the name butane. Now, although these are two different these are two different compounds, they actually have the same molecular formula. Now, there's a unique nature of isomers, and it's that they vary in their physical properties. They vary in physical properties like melting point, as well as boiling point. These physical properties vary for isomers, and you'd expect that for boiling point and of course melting point, if you just taking a look at this structure, from the way in which this structure is configured and from the way in which it's arranged, we can see that this structure occupies a larger surface area. It occupies a larger surface area, and this occupies a smaller surface area. This simply implies that it will take more amount of heat to raise this molecule to a temperature as compared to the amount of heat it will take to raise this. So it's expected that for two given isomers, the one with more branches has less boiling point as compared to the one with fewer branches. So this is the idea, just the general idea of isomerism in relation to alkanes. Now, when we're looking at when we're taking a look at alkyl groups, I did mention that depending on the position from which the hydrogen is removed, a given alkane can form more than one alkyl. Now, a good example, or the way in which to view this, is given the compound methane, which is CH4, and given the compound ethane, which is C2H6, also giving the compound propane, which is C3H8. Now, if we are to draw out the Lewis structure of these three compounds, now of course we are already hinging into representation. Now, if we are to draw out the structure of these three organic compounds, this would be represented as this would be represented in this way, and this would be represented in this way. The hydrogen atoms would be distributed equally, so each of the carbon would have 3, and in this case would have something like this. Now, this is to drive home the point of isomerism in alkyl. Now we are looking at isomerism for alkyl. Now, earlier we said that the general molecular formula for the alkyl, even though the alkyl actually exists as radical rather than molecules, but the general formula is CnH2n plus 1. Simply put, it has one less hydrogen than its corresponding alkane. So if we want to form methyl, which is the corresponding alkyl for methane, we simply take out one hydrogen. Now, since all of these hydrogens are in quotes the same, we could actually remove any one of these hydrogens. So we could decide to remove this one, we could decide to remove this one, or this, or even this. Now, no matter the position from which we remove this hydrogen, we would always form methyl, which is CH3. Now, why is this so? We would always form methyl regardless of the hydrogen removed, because all of the hydrogen atoms under consideration are actually identical. They are identical in the sense that they occupy the same environment. Now, how do we mean by they occupy the same environment? Now, each of these hydrogen is attached to a carbon atom that is attached to 3 other carbon atoms. So if we consider this hydrogen, this particular hydrogen is attached to this carbon, and this carbon is attached to 3 other hydrogens. If we consider this with respect to this, there's a carbon attached to 3 other hydrogens. So the environment is basically the same. A very clear way to see it is from the condensed formula. Now, looking at representation, a way to represent organic compounds is by use of the condensed formula. So the condensed formula would simply, for methane, is simply CH4. This is the condensed formula, and it's also the molecular formula. Now let's take a look at ethene. Now for ethene, we have 6 hydrogen atoms. Now, no matter the hydrogen atom that is removed, be it this, or this, ethene would always form ethyl. Let's take a look at the condensed formula. The condensed formula for this would be, how we draw the condensed formula, would look at that under representation, but the condensed formula is CH3, CH3. Now notice that for the hydrogen is actually attached, 3 hydrogens are attached to each of the carbon atom, so the environment is the same. How we can picture it is that if we have take the carbon atom to be a man or a woman with 3 children, and this carbon atom is also a man or woman with 3 children, being the hydrogen. So if we take out a child from this carbon, that child, being 1H, is coming from the same environment as one child from here, because each of these children, if a child is taken from here, that child will have 2 siblings, and if a child is taken from here, that child would also have 2 siblings, which are the 2 other hydrogen atoms. So basically all of the hydrogen atoms have an identical environment. However, what we have actually been waiting for is actually to take a look at propane. Now propane, the condensed formula for propane is CH3, CH2, CH3. Now in this case, as in contrast to methane and ethene, where we said irrespective of the hydrogen removed, would always form methyl for methane and ethyl for ethene. Now for propane, the case is different. Now if we look at this particular hydrogen as compared to the hydrogen attached here, these 2 hydrogens are attached to a different environment as compared to here and here, and you can also picture it as thus. If we remove 1 hydrogen here, this particular hydrogen being removed would have 2 siblings left in quotes. Same thing applies here. However, if we remove a hydrogen from here, that hydrogen would have 1 sibling in quotes. Okay, so this hydrogen is coming from a different environment as compared to these two, meaning that if we remove the hydrogen from this environment, we would form a different alkyl as compared to if we were to remove it from here or here. Now, this is the general idea of isomerism for the alkyl group. And just to visualize it a bit more, let's take a look at propane. So this is propane with the hydrogen and the hydrogen moved here. Now, if these are the hydrogen atoms. Now, if we want to form an alkyl, and by so doing we eliminate this hydrogen, the alkyl formed is not propyl. The alkyl formed is actually isopropyl. And this is because the environment from which this hydrogen has been removed is different from these two environments. However, if we were to eliminate the hydrogen by removing the hydrogen here or any of the hydrogens here in this environment, what we will form would be propyl and not isopropyl. So to write it as a condensed formula, if we were to have CH3CH2, okay, meaning we're eliminating from here. Okay, if we're to eliminate from here and having this is going to be called propyl. However, if we're to eliminate from here such that we have CH3, of course the methyl group or the alkyl group would be attached to the longer chain from here, and then CH3. Now this is isopropyl and not propyl. So this is the idea of isomerism for the alkyl group. Now let's move on to look at representation of alkanes. How are alkanes represented? Alkanes could be represented by molecular formula. They could be represented by their structural formula. The structural formula. We also have the condensed formula. The skeletal formula. And for this video, we'll be looking at these four representations: the condensed, the molecular, the structural, the condensed, and the skeletal. Now since we have already established that the general formula for the alkane is CnH2n plus 2, let's take n equals 5. Now for n equals 5, would have the molecule C5H12. Now what we have here, what we have established here, is what we call the molecular formula. So this is one way to represent organic compounds, or to be specific, alkanes. This is one way to represent it. So the molecular formula tells you the exact number of atoms of an element present in a molecule. Okay, we also have the empirical formula. So if we have, for example, N to be equal to 4, and we end up having the molecule C4H10. The empirical formula would be the formula that would give you the number of atoms in the lowest term. So this would be represented as C2H5. That is reducing this to the lowest term with a 2 outside the bracket. So this would be the empirical formula. However, the molecular formula tells you the exact number. So for C4H10, the molecular formula would be this, and the empirical formula would be this. Now, how about the structural formula? The structural formula could also be called the Lewis structure. Okay, so for C5H12, the structural formula would look something like this. Okay, of course, with the hydrogen attached, we'll just fill this up. Carbon would generally form 4 bonds, so would fill up the gaps until each carbon atom is attached to 4 elements. Okay, so this would be the structural formula in this case. This would be the structural formula. Now, the condensed formula, how we draw the condensed formula goes like this. Consider each carbon atom. Consider each carbon atom in the longest chain. So the first step to drawing the condensed formula is to consider each carbon atom. Consider each carbon atom in the longest chain. Okay, then consider the substituents or the hydrogen atom or hydrogen atom attached to it. So in this case, this is our longest chain. So from the structural formula, we have the condensed formula. Now in this case, our longest chain is this. So we have to consider each carbon atom in the longest chain. So we have the first C. Now we have considered the first C. Consider the substituents attached to it, or the hydrogen atom. Now the hydrogen atoms attached are 3, so H3. Considering the second, it has 2 hydrogen attached, so CH2. The third also has CH2. Same thing applies to the fourth, CH2, and the last has CH3. Okay, we'd still go over the condensed formula for when it has substituents. So for the skeletal formula, now the skeletal formula makes use of 3 things. The skeletal formula makes use of 3 things, and would consider these 3 things as follows. It makes use of ends, bends, and intersections. Now in the skeletal formula, it's also called the line angle formula. Line angle formula. So it makes use of lines, and whenever we have the end, or we have an end, a bend, or an intersection, these 3 points represent a carbon atom. So if we have an end, there is a carbon atom there. If we have a bend, there is a carbon atom there, and if we have an intersection, there is also a carbon atom there. Now for C, or for pentane, as we have considered, okay, for pentane, as we have considered, a way in which we would draw out the skeletal formula for this would be, it makes use of zigzag basically. So zigzag line. So we'd have 1, 2, 3, 4, and 5. Okay, so each end is a carbon. There's a carbon here at this bend, there's a carbon at this bend, there's a carbon at this bend, there's a carbon, and at this end there's a carbon. So we have 5 carbon atoms. Now in a case where we have only carbon and hydrogen, we simply use lines. But if, take for instance, we have if we have a chlorine, for example, attached maybe somewhere here, if chlorine is attached here, it would simply be indicated like this. Okay, so a bend such as this, or an end such as this, represents a carbon atom. In a case where we have an intersection like this, it interprets that as a carbon atom that exists here. And of course, since we have an end here, there's a carbon there, a carbon here, a carbon here, and a carbon here for those 4 ends respectively. Now this is the idea of representation. Organic compounds, or to be specific, alkanes, can be represented in these 4 ways: molecular formula, structural formula, condensed formula, and the skeletal formula. Now I said we'll take an example for the skeletal formula, or rather for the condensed formula once again. So if we have something like this, and we have here a methyl group, okay, and take for instance we have here chlorine, and I would just fill in the rest, would be assumed to be hydrogen attached in the rest of the carbon. Now would consider the longest carbon chain, okay, and in this case the longest carbon chain quite evidently is this one. Okay, we have 1, 2, 3, 4, 5, 6 carbon atoms, and if we're to go this way, would still have 6 carbon atoms. So it would be 1, 2, 3, 4, 5, 6, but would rather take this route. Okay, so considering that to be the longest carbon chain, we have here a substituent in the form of an alkyl group, which is methyl, and we have substituents here as chlorine. Now how do we draw out the condensed formula for this? Remember, the first step is to consider the longest carbon chain, then consider each carbon atom in the longest chain, and then consider the substituents or hydrogen atoms attached to it. Now the first, if we number starting from here, would have 1, 2, 3, 4, 5, 6. So the substituents would have the numbers 2 and 5. Now let's number from the other end and see if we have lower numbers. In this case, we would have 1, 2, 3, 4, 5, and 6. So at the end we would still have 2 and 5 as our numbers, but preference is given to non-organic substituents, and in this case a non-organic substituent would be chlorine. And so rather than starting in this direction and giving methyl a lower number, which is 2, would start in this direction and give chlorine a lower number, which is 2. So this particular carbon, or this particular compound, of course we don't need the numbers, but it's just good for us to know that preference is given to non-organic substituents given particular compound. Now, starting from this end, would consider the first carbon, which is C. This carbon has 3 hydrogens attached to it in this way. So it has 3 hydrogens attached, so CH3. Now the next carbon, which is C, has 1 hydrogen attached, so H, and then it has a methyl group attached. Now because the methyl group actually exists as a radical, we place it in a bracket, okay, CH3. Now consider the next carbon. It's attached to 2 hydrogens, so CH2. The next is also attached to 2 hydrogen, CH2. The next carbon is attached to 1 hydrogen and a chlorine, so CHCl, okay, to indicate chlorine. And the last carbon here is attached to 3 hydrogens, so CH3. Now this is the condensed chemical, or the condensed formula for this particular compound, okay. So with these 2 practices and with further practice, we should be able to give the condensed formula for compounds. So that's that on representation. Now moving forward to properties of alkanes. Now we know that alkanes are organic compounds, okay? They are organic compounds. And another thing that we know by now is that alkanes are formed by covalent bonds, okay? Alkanes are formed by covalent bonds that exist between carbon and hydrogen. Now, what this simply means is, based on solubility. Now, a general law of solubility is that like dissolves like. What this means is that if we have a polar solvent would dissolve a polar solute. And if we have a non-polar solvent would dissolve a non-polar solute. Now, alkanes are covalent and they are non-polar covalent, majorly non-polar covalent. This simply means that they are insoluble in polar solvents, and the universal solvent that we know to be water is a polar solvent. It means that alkanes are generally insoluble in water. This is one property of alkanes. Now, we also have seen the general formula for alkanes, CnH2n plus 2. Now, from our idea or from our knowledge of intermolecular forces. Now, intermolecular forces are forces that help to bind molecules together. They exist between molecules, and not within molecules but between molecules. So if we have molecule 1 and molecule 2, the force keeping these two molecules attracted together is the intermolecular force. Now the intermolecular force for alkanes is a dispersion force, and this dispersion force increases as the size or mass of the molecule increases. So going from 1 to say 20, so, or let's take a smaller value from 1 to 10, methane being CH4 to C10H22. Okay, this has a lower mass as compared to this. So it means that the dispersion force or the intermolecular force that exists between methane is lower as compared to the force that exists between the alkane molecules. And this plays a role in the physical state of these organic compounds, because of course the higher the intermolecular force, the more likely it is for that substance to be solid. So generally, alkanes from n equals 1 to n equals 4, that is from methane to butane, are gases. And then from 5 to 17, so 1 to 4 are gases, 5 to 17 are liquids, and from 18 and above we have solids. Now some texts actually have that even from a number like say 14, alkane actually exists as solid. So this varies to an extent. It's not necessarily 5 to 17. So the two properties that we can take away from this explanation is that firstly, alkanes are insoluble in water, and the higher the molar mass, or the higher the mass in general, the stronger the intermolecular force. And that implies that as we progress in terms of the value of n, we would move gradually from gaseous states to liquid and then finally to solid. Now the next thing we want to consider is the chemical reactions that alkanes undergo. When we started out with water alkanes, we stated that alkanes are saturated hydrocarbons, and I also explained that this means that they cannot take in more than they already contain. Okay, they cannot undergo addition reaction, and if anything needs to be added in any sort, something would have to be taken away in order for it to be replaced by another. So alkanes undergo substitution reaction, they undergo combustion, just like every other hydrocarbon. They undergo combustion, they undergo for the sake of this video anyways, we'll be looking at substitution and combustion basically. So substitution would be looking at substitution using halogens or halogen substitution. Now given an alkane like methane with the formula CH4. Now substitution is basically removing a hydrogen atom, in this case a hydrogen atom, and replacing it with a halogen atom. So giving C H H H and another H. Now we are going to add chlorine, and this would give us this one of the, since chlorine is diatomic, one of the atoms in the chlorine molecule would displace this and take its position, so would form something like this, that this is a C. Okay, this is C H H H, and then Cl, and what we'd have here would be hydrogen chloride. Okay, now this reaction is photocatalytic. This substitution reaction is photocatalytic, and although the word seems it seems big, it simply just means that it takes place only in the presence of light, and not just any light but ultraviolet light. So ultraviolet light helps to catalyze this reaction, or in essence it simply helps to form radicals out of chlorine. So rather than having chlorine as a molecule, the ultraviolet light helps to break the chlorine into radicals so it can take the position of hydrogen and be substituted into the molecule. The next reaction that we want to consider, of course, is combustion reaction. So for organic compounds and for hydrocarbons to be specific, they undergo combustion reaction to produce carbon dioxide and water vapor. Okay, water vapor in the presence of abundant or excess oxygen. So combustion is just a fancy word for burning or addition of oxygen. So if we're given CH4 and it undergoes combustion, which is addition of oxygen, it would produce carbon dioxide and water vapor. Okay, now this is when oxygen is in excess. If oxygen is limited, however, rather than producing carbon dioxide, it would actually produce carbon monoxide. And that's why we're always advised to burn fuel in a well ventilated place where there is abundant oxygen, because otherwise we would form carbon monoxide, which is actually a toxic gas and it could cause suffocation. Now, what I want us to take note of under combustion is the general formula for combustion. Now we're going to do a bit of derivation for this. So given a hydrocarbon with the formula CXHY, so we're given a hydrocarbon in this form, CXHY. Now for an alkane, of course, we know that X is going to be equal to N and Y is going to be equal to 2N plus 2, since the general formula for alkane is CnH2n plus 2. By comparison, X is N and Y is 2N plus 2, but would rather make use of this. Given this to be the general formula for the alkane, it reacts with oxygen to produce carbon dioxide and water vapor. Now, what we are about to derive is an expression that would give us a balanced equation for any given hydrocarbon. Now, what we want to start with is include coefficients or attach coefficients to each molecule in this equation. So to chlorine, or rather to this hydrocarbon, I would attach A. So A CXHY plus O2 would give CO2 plus H2O. So I would attach a B here, a C here, and a D here. Now this is the general way to balance a chemical equation or a chemical reaction. Now for carbon, on the left hand side, AX is equal to, on the right hand side, C. For hydrogen, on the left hand side, AY is equal to 2D. For oxygen, 2B is equal to 2C plus D. Now we're going to make an assumption, and our assumption would be that let A equals 1. So if A equals 1, then X equals C. Okay, which implies that C equals X, right? Now, given that C equals X and A equals 1, we could also apply A equals 1 in this case. This would mean that Y is equal to 2D, which implies that D is equal to Y over 2. Now we could substitute C and D in this case. So 2B is equal to 2C, which means C being X, plus D, which is Y over 2. This means that 2B is equal to 2X plus Y over 2. Dividing through by 2 would have that B is equal to X plus Y over 4. So we have our values for A, for B, for C, and for D in terms of X and Y. So let's write this out. It out, CXHY has the coefficient of A, which is equal to 1, so we could just write it out as CXHY plus O2 has the coefficient B, and B is X plus Y over 4 O2, giving us C here is equal to X, so X CO2 plus D is Y over 2, so Y over 2 H2O. So now let's assume that we're making use of methane, and methane being CH4. Okay, now in this case it means that X is equal to 1 and Y is equal to 4. So CH4 plus X is 1 plus 4 divided by 4 O2 would give us X, which is 1, that's CO2 plus Y 4 over 2 H2O. This is going to be CH4 plus 4 divided by 4 is 1, and 1 plus 1 is 2, that is 2 O2 and this would give us CO2 plus 4 divided by 2 is a 2H2O. Now we can clearly see that this is a balanced equation. So what we have been able to derive is a general formula for combustion that would give us a balanced equation. Okay, now finally let's take a brief look at the uses of alkane. Okay, some of the uses of alkane. So alkane is used in our houses, our household, is used. Kerosene that we use is actually an alkane. Kerosene is an alkane. The cooking gas we have at home, liquefied gas, is also an alkane. So this is just like very briefly kerosene, cooking gas. There are a lot of other uses of alkanes, and yes, basically this is what this video is about. Just a general overview of alkanes, their nomenclature, isomerism, representation, properties, and so on. Please, if you liked this video, if you enjoyed this video, if you learned something in this video, please give it a thumbs up and ensure to subscribe.